I do want, as we lead into today's lecture, this was a perfect lead-in. It came from the quiz. A couple of people on the short pre-quiz asked the following, I think, very reasonable questions that actually I was going to comment on anyway in my introduction as we move forward from kinematics to forces. And it has to do with this idea of what a physics problem is like. You know, give us more practice problems so we know how to solve all the problems that we could ask, that I could ask. I never encountered the last problem in the midterm. Now, if you actually go back and look at the solution to the midterm, and this is where physics is so different in so many places and other topics, and at the same time so challenging, right? What we have finished is 3 weeks of kinematics. Now, what you hopefully got out of those 3 weeks in doing the problems is the following important sense. There is a class of problems that are related to describing motion. And those have questions like, where do you land? Where are you? How far did you travel? How high did you travel? How fast did you travel? And what direction? And we focused on this special case of constant acceleration and basically used our two derived equations, definitions, however you want to look at it, for answering these questions. And why do we do the different types of problems? You know, the challenge is there's actually an infinite number of variations. There is, unfortunately, as much as I would like to, no way I could do this. There is no way I can achieve assigning and doing an example of every possible individual problem that comes from the class of problems that are kinematics. And the switch you have to make in doing physics, and it only really makes sense, I said it at the beginning of the class, but it only makes sense really after you've experienced it once, is there was really only one problem we ever did. We did projectile motion. And motion in one dimension was projectile motion that didn't go up in the air. Okay? So there was really only one type of problem we did, constant acceleration. We did lots and lots of variations of it. And if you think of every single one of those as a different problem that you need to know how to do that problem, it will be very hard to be successful in this class. But if you do enough of them that you have that realization and you're going into it thinking, why are these all the same? Why are these all the same? And you make yourself realize why they're all a single problem, just with different variations, then it will be impossible for me to give you one you've never seen. Because you will realize it is one of this class of problem, and I know how to do it. And that becomes really important as we add our other two classes of problems. And what we are working on, we started a little bit last week, and we're now going to spend this week and next week focusing on, are the class of problems involving forces. So here we were focusing on describing the motion, asking where, how far, how high, how fast, what direction, learning the type of questions to recognize that it was kinematics and that class of problem. What are the types of questions we will get in forces? In forces, we're going to be asking things about the cause of motion. So you might have questions like, do you start to move or stop moving, right? To start or stop moving, this requires an acceleration that's not equal to 0. This requires a cause of that acceleration, so it requires a net force. So it is a force problem. And that's very different than asking, how fast are you moving, where are you moving? It's a, do you start to move? Is there a cause to your motion? Is there an acceleration that is generated? The more obvious ones are when we ask the straightforward question, what is your acceleration? Right? It might just be given in the problem, but that's unlikely if you're being asked it. You're being asked it because you'll know the causes of that acceleration, the forces, and you'll want to compute what it is. The other type of question is, does something, usually a rope, break? Right? That's a cause of something happening. A force gets too big and the rope breaks. Though these look like different questions, they're all basically the same physics idea and physics class of question. The other one is, what force is needed to whatever it is? Accelerate, have a constant acceleration, just start to move, just stop. And at the end of the day, for all of these, you will use the same three laws, Newton's laws. The first law you won't even realize you're using, because it tells you that you have the correct reference frame, that it's an inertial reference frame of constant velocity. We do very, very, very little where we have to worry about that. That would be in a more advanced physics class. But it's there behind every problem we do. What we focus on is the second law, F equals ma, because that tells us what happens to a single object. And keep in mind that you sum up all the forces for the single object for its acceleration. And we will use Newton's third law, because that will give you all the forces or interactions. That are between objects. And you will use these to feed into here, to F equals ma. So as we go forward, the next week or so, I will be doing some demos. I will be doing a bunch of example problems. Today I will kind of lay out the big picture. And in all of that, again, learn the lesson from kinematics. Don't focus on each problem as a separate, different problem. Ask yourself right from the beginning, how are all these problems basically the same? Yes, little details will vary, right? If you're solving for something just to move, you're solving basically for an acceleration of 0 that's about to become non-zero. If you're solving for a constant acceleration, you're solving for a number. Those details matter. They do make it a little harder. But the way you have to think about it and approach it is, we are now doing this class of problems, how things move. And we can, because we are dealing with accelerations, connect this all the way back up to a description of motion. Right? Acceleration is both something that we use to describe our motion, and it's the thing that's caused by forces. So now we have two classes of problems that can be connected. So in the same problem, you might need to use kinematics for one part of the problem and Newton's laws for the other part. And you have to now recognize not only two classes of problems, but when a single problem involves two types of problems. And by the end of the course, we're going to add a third piece, energy conservation. And that's basically it. We're going to have those three classes of problems: kinematics, describing motion; forces, cause of motion; and energy, which is kind of in between the two. It involves both causes and description. And they can interrelate with each other, and all three of those can interrelate, or a problem can be just one of those three. And that's how you want to be approaching this class. So hopefully that makes sense. I really was looking, I was really glad I got those two quotes, because it gave me a chance, I was going to do it anyway, to really emphasize, now that you've had this experience, what it's really about, because it only gets harder as we go on. That's the bad news. Any questions on that? Okay. Now, this is an interesting set of chapters, because really what I'm going to do is kind of two things. Today, I'm going to briefly mention all the key ideas in chapters 4, 5, and 6.1 that you're going to need over the next week or two to do the homework. If you look at the homework assignment that's due Sunday, it's one of our longer ones, and it really covers stuff in all of these places. Parts of Chapter 4, all of Chapter 5, and Section 6.1. Now, why does it do this? It's because we need to learn to recognize the types of acceleration and the types of forces. But at the end of the day, all the problems we do, we use the exact same method and technique independent of what types of forces and accelerations show up in it. So it's kind of this weird thing. So what I want to do is right off at the bat today tell you about all the forces and accelerations you'll meet over the next week. So you have them in front of you to look forward to. Do a little bit and show you how we would solve any given force problem in general with a particular demo example. And then I'm just going to do bunches of examples and demos for the next few days that'll combine these different forces in different ways. So a very good idea is to start reading the chapters and start the homework kind of in order, because it does build. If you do the earlier stuff, there's only one or two types of forces. As you get to the later stuff, it can involve any of the forces we've learned up to that point. If you wait till the weekend to do this homework assignment, it will probably be too late. So you definitely want to build with the week on the homework and with the class. Any questions? So these next two parts of the lecture will be very, very useful to come back to, because they're going to be the two key lists that we're going to have. And I'm just going to start with a whole new piece of paper. And list 1 is accelerations. And the reason I do this is let's go briefly to our online quiz that you're going to have to go back to. This is going to open up, and I'll reopen it tonight, the second version with the same questions, but I'm going to remove, like it's showing you the answers. The second version will be due Friday, at the end of when we've covered all this stuff. And if you notice as we go through, there's some key ideas to look for. What's this whole friction thing, moving at constant speed, going up a ramp? This question number 1 is about the fact that if I'm going up a ramp, there's friction, there's gravity, and there's what I'm pushing with. At a constant velocity, what is your acceleration? 0. So what should all the forces do? Add to 0. This question gets at the fact that since I only mentioned 2 of the forces, I'm missing gravity, I have to push with a greater force than friction, because I'm also canceling gravity. So one of the key things is practicing finding every single force in a problem. You always have to do that first, and we're going to practice that. This next one, so the only weird force we meet is the force of static friction, because the force of static friction can change its value. And that's going to be something that's going to be the hardest conceptual challenge in this week. And so this question gets at that, and so you'll want to look into how that works. The most common mistake is something that's in problem 3 and 5. I use the word here on purpose. Centripetal forces do not exist. Centripetal accelerations exist. And if you have a centripetal acceleration, there must be a bunch of forces that add up to cause that. Some people like to refer to the total net force that causes the centripetal acceleration, the centripetal force, which is okay. But it's very, very dangerous, because I can guarantee you, if you are thinking in terms of the centripetal force, you will put it in your free body diagram. You will write it as mv squared over r. You will put the acceleration as mv squared over r. Those two will cancel out, and you'll get the problem wrong, because there is no force mv squared over r. There's no physical force. The physical forces are always the normal force of a wall, friction, a rope pulling on you, gravity. There's always some other real force that's causing the centripetal acceleration. And if you think of centripetal force as a force in your list of forces, you will get an extra force. And so that's very important. So that shows up here in the road one. And it shows up here in the loop-the-loop. So you'll want to look at those. And then this last one, again, has to do with keeping in mind breaking things into components, what's happening in all the directions, and what cancels. Because there's lots of problems early on where the normal force does equal the weight. And so people start to think, oh, the normal force always equals the weight, because it's equaled the weight the last 3 times I've done the problem. But it doesn't. That's just what happens in some of our initial warm-up problems. So you have to be aware that the normal force is not actually equal to the weight. It's its own force, and you have to deal with it that way. So these are things you want to look for as I make my list and as I go through the examples. So that's why for this week I wanted to put that pre-quiz up and then give you the same quiz later, because these are such important concepts. I wanted you to have a chance to experience them ahead of time without worrying about getting them right, and then kind of go forward with it. Questions? So, let me ask you this. How might you know what the acceleration of an object is? Yeah, but how might you know? What are some ways you find out in physics problems about the acceleration so far? If I'm given velocity, use the definition, you take the derivative. But there's a more common way.
Find the net forces and then divide by the mass.
Yeah, you can do that, but there's an even easier way. I heard it. It's given. This is the most common way to know the acceleration. It's one of the few things that is least likely to use a formula. And it'll be given to you usually as some constant that's not equal to 0 or 0. That is a very common situation to have. Now, there's a subtle way it can be given to you. You can be told you're just about to move. To actually start moving, what do you need? If you are at rest, and in the next instant you're going to be moving, what does that mean you have? You have an acceleration. If you're just sitting there at rest for some time, what is your acceleration? 0. So to just about move means you go from a equals 0 to a not equal to 0. The only number we can solve for, there's no number we can agree on that's bigger than 0 to solve for. So the physics trick is you're always going to be solving for a equals 0. But you're going to be solving for it in a situation where there's some force that can change value. And it wants to reach the value so that a will exactly become 0. So simple situation, right, is if I'm going to lift something. Say I'm going to lift this up. Right? I can apply lots of little forces where it won't lift. But there will be some force that is the biggest force that will still have 0 acceleration, but if I make it any bigger, it'll now accelerate. And so that's the sense I'm solving for 0. Make sense? It will as we do more problems. But that's the tricky one. And then the final one is section 5.2 of the book, centripetal acceleration. Two ways to approach this. One, you can memorize the formula and not think about it too much. But it's very helpful to have a picture of what's going on with centripetal acceleration. Centripetal acceleration occurs anytime you turn. It's particularly useful for constant speed in a circle. And notice what happens. If I'm moving with v1 here, and at some later time I'm moving with v2 over here, and I want to ask for my delta v, which is v2 minus v1, v2 is like that, minus v1 goes in the opposite direction, So delta V is basically pointing radially inward. Right? As I go in a circle, no matter what circle I move in, my velocity, by definition, is changing towards the center. My velocity points more towards the center than it did before. This is a little hard to picture because the velocity itself is always tangent to the circle. Right? So the velocity actually never points towards the center. It's the change in velocity that points towards the center because I'm turning in the direction of the center. And that's what you have to picture. Now, to get the magnitude to derive it, I'm not going to derive this formula. It's in the book. Okay? It uses the basic triangles and stuff. But you can find this change in velocity in some time, and you see that it has to do with the radius of the circle and the speed you go at. So the smaller the radius, the bigger the acceleration. And this is the key trick behind designing a roller coaster. If I can make really sharp turns with small radii of curvature, small circles, then you will feel a big acceleration in the roller coaster, and it will be more exciting, even if I'm going at the same speed as another roller coaster. Because what we really feel on the roller coaster are the accelerations. And that's why the more twists, the more turns, the more loops, the more exciting the roller coaster. Any questions on that? It'll become more obvious as we do the problems, but this is it. These are the three ways we get accelerations. So when you're reading a problem, you're asking yourself, do I know the acceleration already? And I'm going to know it because one of these three things happen. They either give it to me, they tell me I'm just about to move, or they tell me my speed of moving in a circle. If they don't tell you one of these three things, you're going to have to find it using F equals ma if it's something you need in the problem. Any questions? Okay, our force list is a tad longer. So for forces, I'm going to actually mention the one in chapter 6.1 first. That's gravity. That's the famous Newton's law of gravity. If I have a mass 1 and a mass 2 separated by some distance r, then the magnitude of the force is Newton's gravitational constant g, just a number, m1 times m2 over r squared. And the direction is attractive, meaning the force on mass m1 is towards m2, and on m2 is towards m1. It's an attractive force, equal and opposite. Now, one thing you'll notice, constants like g, numerical constants, and that's, I think, the only one we get, I will give you on the test. So if there's ever a Newton's law of gravitation, I don't expect you to have g memorized. Now, there's a special case of gravity, which is section 4.6. This is gravity near the Earth's surface due to the Earth. We call that weight. And its magnitude, we can plug in, since the mass of the Earth, the radius of the Earth, and g don't change, we plug those in, and then we get our mass here. We can figure out what this number is, and this turns out to be little g, which is 10 meters per second squared. So the weight is given by mg. Do not confuse this with Newton's second law. It looks like it. From it, we can find out that the acceleration due to gravity near the Earth's surface is g, which we already used. But it's a very different idea. This is just a calculation of the force from the definition of the force due to gravity. But it's another force we have, and we do very little with the first version of Newton's law. We don't do many of those problems. Most of our problems take place near the surface of the Earth, and we're going to worry about this version of the weight and just use mg for the weight of an object. The next one is really one force that we break into two. Whoops, I can't spell. is contact forces. If two objects are in contact, there is an equal and opposite force between them. So here's object A, here's object B, and if you recall, we can break everything into two directions. We can make one that's perpendicular to the surface between them, and a direction that's parallel to the surface. And when we do that, we get two forces. The perpendicular contact force we call the normal force. There's no formula for it. It's just when two objects push together, there's a force perpendicular to the surface. We call it the normal force. It always exists for anything in contact. The parallel force, and that is section 4.6. The parallel force, the parallel component, is friction. And that's section 5.1. It does not always exist. In physics, we imagine frictionless surfaces. And there's some things that approach it. Ice moving on a table is basically frictionless. Pucks on an air hockey table, right? The little bit of air gives you a frictionless surface. So you can actually get real close to that. Friction, by far, I think, is the hardest force that you will deal with. And the reason is, there's two types. There's static, and there's kinetic. So you first have to know which you're using. Notice some key pieces. Static has a less than or equal to. It actually changes its value. And they're both related to the normal force, which does not have a formula for it and might change in the problem depending what's going on. So these are two pieces that can cause you problems. The other piece is that it opposes the attempted motion. And every now and then, the attempted motion is not obvious. And that's why you have to think about friction in a little bit of ways. So if I am going to start moving my car, which direction, and I say I'm going to drive this way. I'm going to start moving my car. Which direction is the force of friction acting on me? Is it moving backwards or forwards as I try and start my car? Well, if friction's backwards, how the heck am I going to move forwards? The wheel, think about, this is where it's horrible. What is your wheel doing? Your wheel turns like this to move you forward. Your wheel is trying to slide backwards on the ground. Your foot, to move forward, is trying to move backwards. My attempted motion is actually backwards when I want to move forwards. So friction acts forward and moves me forward. Because the attempted motion you want to focus on is the attempted motion of the two objects in contact. Right? All friction knows about is my foot touching it. And my foot tries to move backwards, friction acts forward. Now when I stop my car, what motion is being attempted by the wheels or my feet in the ground? To slide forward. So which way is friction going to work? Backwards, and it's going to stop me. And that's why friction, by far, is going to be the thing that costs you the most pain. And literally, right, if you're up, never mind. So you've got all of these issues with friction. The final last force we meet is pretty straightforward. It's tension in strings. And it's any time I push or pull. Now, pushing and pulling, you can often think of as a normal force. It's two things in contact. We often think of it separately as just pushing and pulling, but they come together. It is a contact. I realize that was rather, the most boring 30 minutes of our class, but it needs to be done. I really feel if we did each of these one day at a time and you had to read the book through, it would just be a little overwhelming as each one got thrown at you. I think starting with your list at the beginning, maybe make your own list, print it out, have it for you, and as you go through the next week or two, just have it there and be checking, Are these all the forces? Did I find all the forces? Are any of these not here or any of these here? There's not going to be some other magical force that shows up in a problem. If you've gone through the problem and every single one of these is there and you have your free body diagram, there really can't be anything else. Now, there might be 6 normal forces because the object you care about might be touching 6 different things. Now, there's never going to be 6 normal forces. That was just to panic you. But there could be more than 1 normal force because you might be touching 2 or 3 objects. There might be 2 friction forces because you might be touching 2 objects. There might be 2 tensions because you might be held by 2 ropes. So there can be more of each of these, but there can't be any different type of force. We ready for a clicker question? Ready to wake up? Okay, I've got 2 masses here on a rope. Oh, I should start the clicker question. Okay, this is really going to work well. I love when the demos fail. That I can deal with, but my inability to use PowerPoint is more embarrassing. Each of these has a mass of 10 has a mass that will give you a 10 Newton force. Now, they're hanging on a rope, and there's a scale in the middle, and so they're both pulling on the scale. And the question is, what is going to be the force in newtons that the scale reads? So keep in mind, we saw this last week. Newtons are kilogram meter per second squared. They're a unit of force. And so is it 10, is it 20, or is it 5? So basically I'm asking, by having the string, do I get the force of one of these, both of them, or does it somehow cut it in half? Yeah, I don't even know why we're bothering now. 5 more seconds. Three, 2, 1. And as you saw, it's 10 newtons. So we can turn our scale around, and you can see it's 10 newtons. Now, one of the fun things, there's a little bit of friction in here, so occasionally it gets stuck above 10 newtons. But if I knock it around, it's on 10 newtons. Now, what I'm going to do is I'm going to take this mass off and hook it to the scale so that the scale is only having a pull from this mass. So the situation is like it's connected to a wall, and then it's being pulled on by our 10 Newton mass. So now that we know both give a force of 10 newtons, the question is, so this is the question now with 1 mass. And I'm serious, that really was just a typo. I have to go change that. So now when I take off the 1 mass and do it with 1, what is the scale going to read with 1 mass? Wow, today must be the day for total PowerPoint failure. And very interesting. We're not sure. Nicely spread out. Now, what I want to do, before I show you the answer to this, let's see if I can make this work. How do we approach these? The way you're going to do all of these problems, and it's so important that if you, everybody always asks me this, do I really have to draw a free body diagram? Yes. On the free response question, I'll just tell you right now, if you do not draw the free body diagram, you will lose points. I don't care if you get the problem right. The reason being, I want to know that you can show me all the forces, and that's the best way to do it. So we do what's called a free body diagram. This is our key tool. It's the main thing we do. The way you do it is you take your object, and you're basically now using the third law. And you ask the question, what does it interact with? So, our mass hanging here on this string, I will tell you right now, has 2 interactions. What are the 2 things it is interacting with? Well, it's not really interacting with the ground. You have to be careful. We use that phrase for something that's actually touching the ground. What is it interacting with? We call this big thing that we're standing on The Earth. Gravity is the interaction. The Earth is the thing we're interacting with. It just helps us to use that same common language. So it has an interaction with the Earth, so we draw that in. The interaction with the Earth is always straight down in the vertical direction, and we like to call it the weight, so F sub W for weight. You will see lots of different notations. F sub W, just the capital letter W, and F sub object A with the Earth. There's lots of ways it'll be written. Now, it has one other interaction. What is it? The rope or string pulling it up. I most often use, and it's probably the most common, a sub T for tension. So the T is tension. But sometimes there will be problems where that's not quite as clear, and you will use a sub R for rope. There will be different ways you do it. Some people will just write that as a capital T. So there are these two interactions. Once we know all our interactions, we then apply this to F equals ma. If the object is not moving at all and just hanging out there, and its velocity is not changing, what is A? A in this case equals 0. We pick a direction to be positive, so it's very common to write these now as just their magnitude and put the minus sign in by hand. So that minus sign is the direction for the weight. And we plug in our 0 for acceleration, and we have 0. Now, I've drawn it here as we have it. The question I next asked you about, if I was to draw that as a picture, is an object going across a pulley. There's a scale, but it's basically attached to a wall. And I asked you, what force is this scale measuring? So I'm basically asking you for the tension in the rope. Right? That's what's pulling on the scale. So now, having seen that and the way we think about these problems, vote again. What do you expect for the tension when I pull on it? No? There. There's your choices. You can talk to people. We had a little bit of motion towards 10 newtons. Let's see what we get. Look at that, 10 newtons. And I can even pull on it, and it's really 10 newtons. I didn't lock it there. It does move. Why is it 10 newtons? Well, let's go back. So now I can actually click on the answer. See, 10 newtons. Let's go back to our pictures and our what we call our free body diagrams, right? In either case, let's look at our three pieces, right? There's our scale, and the scale goes to something else. Whether I have a mass over here or not, if I want to draw the free body diagram for each of these objects, the free body diagram for A had tension up, weight down. The free body diagram for B just has two tensions in the equal and opposite directions. And one of the things that happens, there's a little bit of a trick here that you're going to have to know how scales work, and we'll show you in a minute. Both of these had an acceleration of 0. So what that told us in The first one, let's redraw those. So for object A, we had F tension Fw, and we had acceleration equals 0. So F tension, and we're taking up to be positive, minus Fw equals 0. And I told you the weight was such that mg was equal to 10 newtons. So F tension is 10 newtons. For our scale, whether it was attached to the wall or the other mass, the only choice here, again, A equals 0. If I pick that to be to the right, I have F tension minus F tension equals 0. Let's suppose I didn't think they were the same to begin with. I now found out that they're the same. T1 equals T2. And so what you need to know is the way the scale works, right, is if you look at it, this isn't doing anything, and the scale is only pulled on one side. And that's how all scales measure their forces in the rope. So it's not like the scale is measuring the 10 plus the 10. The scale really just measures the 10 it's being pulled with. It measures the tension in the rope. There is a single tension in the rope, and it is equal to our 10 newtons, because this T1 was what connected to that by the rope. This is the hard features of ropes in physics problems. So let me just show it to you again in another picture. Let's look at the picture without a scale in there of our two objects on the pulley. In physics, this is one single rope. And I said this very quickly at the end of class last Wednesday. The key feature of ropes in physics is they always have a single tension in them. The tension in the rope can't change anywhere. It's a single object. It has whatever tension it has. So when I draw a free body diagram for object A and object B, I have to start out with a single tension, because I have a single rope in this case. Now, if I had two different ropes, I would have two different tensions. And this is how these two objects are connected. And that's one of the things you're going to want to look for. Are objects connected because they're touching, or are objects connected because there's a rope between them? And that will give you a connection between them where there's a similar force in both diagrams, just in opposite directions. Now, they may have different weights because they're different objects. And so in principle, I have two separate equations now. I take up to be positive. I have F of weight 1 minus Ft equals mass 1 times A1. And F of weight 2 minus F tension equals mass 2 times A2. And now we have, this is rule number 1 of the ropes. The other rule in physics, easy one to remember. If two objects are connected in any fashion, like this, then to move together, they always have to have the same acceleration. If this one has a different acceleration than this one, then the rope either has to break or collapse, because they're going to move different amounts, get different displacements, and the rope won't be moving the same. So you want to have that mental picture. If two things are connected and they're moving, there's no other choice but for them to have the same acceleration. So you may have started the problem thinking you had two different accelerations, but once you realize they're connected, then we apply rule number 2, and A1 equals A2. So we got rule 1 and rule 2. In this case, we are given M1 equals M2. And so therefore, we end up with a single weight, a single tension, and a single acceleration. And things are much simpler. And from there, we can go on and do what we did when A was 0 and find out that that single tension has to equal the weight. Doesn't equal twice the weight, it equals the weight. Now, of course, if I take this and do that, and now come over here and hang the mass right here in the same place, I now do indeed double the force. It goes from 10 to 20, because I now have double the weight being balanced by my tension. I still have F weight down, F tension up, but now F weight is twice as big, because I have 20 newtons there instead of 10 newtons. Any questions on that? So let's ask one final clicker question. Let's suppose you had a block on a mass with friction. How many, and actually I'll redraw it right here. So we have a block, a mass sitting on a ramp, and there is friction. How many forces, when you draw the free body diagram for this block, how many forces are going to be in your free body diagram? 63% of you are there. There will be 3. That's what we're going to start with on Wednesday. We're going to start doing problems like that. Start looking at the homework, and we'll see you Wednesday.